like to thank the organizers for this opportunity, and also the previous speakers. There's things that I will definitely be taking home to Thermo for us to try out in various applications. It's been very fruitful being here. I'd like to, maybe this is a shift of gears, and talk about using Lua for control of instruments, namely mass spectrometers. And I'm going to focus on the last third of the talk, and the third I don't mean the time, but the last organizational third of the talk on use of some concepts from more functional languages to automate assays and compose automations. So, a structure of the talk of what to expect. First, talk a little bit about what mass spectrometry is and how we use Lua to control such an instrument. It's not entirely a trivial problem. Not going to get deep into physics or analytical chemistry, so no real need to worry. It's all going to be qualitative. And for the more computer science heavy folks in the audience, this part will get a little elementary. We'll talk about iterator pipelines and some elementary higher order functions, and then how we might want to implement these in Lua, and two warm-up exercises. Okay, now what do we do with these for instrument control? Finally, onto the meat of the talk, which is how to use these higher order functions and function composition to automate assay optimization on a mass spectrometer. So mass spectrometry, in brief, you separate and quantify ions in a mixture by mass. So you have to generate, before you start even talking about mass spectrometry, you have to generate ions from typically neutral mixture, either gas or liquid. And what you produce is a spectrum. This is in Daltons divided by the elementary charge. So it's a unit called Thomson, which nobody uses, so we call it Daltons. Spectrum, and then we have the quantitative peaks of how much did we give when we were scanning that particular mass. So there's something with a mass of 69, which I think here in this mixture is in a dazole. I don't know what any of these others are. We have 1.28 times 10 to the 7 ions per second, or a little bit less. It tells us what molecules are in a mixture. If you recall, there was a movie, Medicine Man, 25 years ago, and this was the Deus Ex Machina in finding drugs. So you might have actually seen this before. Somebody told me CSI does this as well. I am not familiar with too much of that. Well, one caveat is that we're separating by a mass to charge ratio and not by mass per se. It's an electrical technique. Applications, chemical and pharmaceutical manufacturers, the obvious one. You have synthesis, how much did I make, isn't really there. R&D, what did I make, and again, how much. Process monitoring, food safety, our little water bottles we have in this room say it's enhanced with minerals for fresh taste. You want to make sure that it's not, perfluorooctanoic acid from DuPont, but that's very tasty, but it's, safe things. Actually, some of this is used for monitoring of imports for contamination and forbidden additives, for example. Toxicology, forensics, material science, environmental monitoring, athletics. Thermo actually had the contract for the last 2 Olympics for anti-doping. That most of the steroid samples were run, or the blood samples and urine samples for steroid tests were run on our instruments. Histology, if you want to look for vitamin D levels, testosterone levels, it's an emerging technique there. And you get much greater sensitivity than the traditional methods. And in the less applied space and the more exploratory space, it's the #1 technique of proteomics. And basically everything with an omics there, plus cell biology. And so wherever you see omics, it can be used, and often it is mass spec or fluorescence for the genomics. It is still the number one technology. In the future, you'll see this in surgery. There's already experimenters out there who are looking at cautery smoke. So when they take the electrocautery knife that generates smoke when they're cutting out cancer, they take the vapor out of that and say, well, you know, what kind of peptides are here and what does that tell me about the proteins? And did I cut out all of that cancer? That's still experimental, but we'll see it in our lifetimes. Also, personalized medicines, the random access analyzers. We'll be seeing, I know a few companies have that in the pipeline. A little bit more about it, this is relevant when we get down to the actual problem to solve. The modern standard techniques called tandem mass spec is that not only do we separate things, but then we break up the molecules and we separate them again, we analyze the fragment patterns. So we pick out, you know, let's peak here at 322, and we can then break that up and look at what comes out. And this gives us a more positive identification. Or if you have, in a mixture, let's say you're running a soil sample, you can have multiple. This is going to be all fuzz. If you pick out, then here, you get some selectivity, saying a peak here and a peak here. And you really get to start separating things. Sometimes this is called MS2. You can even do more fragmentation if you have an ion trap. It's much more specific than a single stage mass spec. Excitation is by collision, electron transfer, or laser pulse. Most common in the field is by collision. We ram these things into argon gas, excite them vibrationally and break. It's dependent, that technique, for example, is dependent on collision energy. You have different spectra based on the different techniques. So that all has to be taken into account typically by informatic approaches, trying to find well, what's the most likely match. If you're using a new technique, the database has an old one that's really beyond the scope here. Often coupled with other separation techniques, most commonly liquid chromatography, but ion mobility is also a big one too. Again, we're taking big complex mixtures and narrowing them down. So, getting a little bit closer to Lua here, is that Thermo has two families of instruments that are controlled by Lua. We have the Endura and Quantiva, including our medical diagnostic device, triple quad mass specs, and then the Orbitrap Fusion, which is used in that omics space. The triple quad has two quadrupole mass analyzers, a collision solver breaking things up, and of course the detector, a whole slew of ion optics to get things in. The Orbitrap Fusion has a quadrupole mass filter, an ion trap for mass analysis, which is really sensitive. You can imagine funneling ions in, storing them up, so the weak signal, oh yeah, keep coming, and then analyze it. And then something called an Orbitrap, which is uses a Fourier transform technique. You have essentially a harmonic oscillator field axial meters, and the ions spin around the center, and their oscillation frequency back and forth will depend on their mass to charge ratio. That's a very sensitive technique. It's a resolving power of M over delta M for 500,000. So if you have something that's a 1 kilodalton molecule, you get 0.0002 AU distinction between things. That's smaller than the mass of an electron. So now on to, well, how do we use Thermo? How does Thermo use Lua to control these things? We have a lot going on to the extent where you almost say we don't. Is you have to control a lot of voltages all at once. So there's a DSP that we rely on to do that, just dedicated just for that. And then on the desktop we have a data system. Just a Windows box that had a user interface and data store. In between, we have a dual-core PowerPC system, and then a FPGA used just as a mailbox, back and forth. What we do is on this we run an embedded Lua. We have the C routines that look, they're very basic, and they run a continuous loop, controlling PID control devices, consuming any data that's sent back, and monitoring the system for errors. And then in that loop cycle is execute the next Lua command, execute the next Lua command. To the point where if you're writing for this instrument in the Lua layer, it looks like it's an extension. Everything you do is controlled. Whether or not you are going to take a scan for is controlled by the Lua. So we have to implement, there's 5 parts to do that. First, access to the individual devices, whether we have something on or off, system voltages on the lenses, the getters and setters, implemented objects corresponding to the original to the each device. We have a table of voltage settings that the DSP sees when it has to scan very quickly, much more quickly than if we were setting things manually from the Lua. So we control these separately. So we have non-scanning voltages, and then we have scanning voltages. But those are also exposed to Lua, so we can change them between scans. These are passed on from this virtual cal file to a scan matrix, which is unfortunate terminology. It's just a linear table run of timed voltage settings run by the DSP. That matrix is built up by Lua while the scan is running. So we have one scan being run by the DSP, and here we're building up a voltage table for the next. So this never has to worry about synchronizing the individual devices. Lua does not. This is defined by a smaller set of scan state variables. So really what we expose to the everyday user is a bunch of setters saying, okay, take full scans, take product scans, take this parameters. So people can, in effect, just switch the instrument between different modes with Lua command. We'll see that in the next few slides. And finally, a data query function saying, we'll pull up what was that spectrum, how much would it have at a particular mass, then pull back to the Lua for mathematical analysis. So what this looks like, you take all that complicated stuff and you provide people a very simple kind of control. I was remarking to somebody earlier that we have Lua written house that looks a lot like BASIC, just a for loop over an integer lattice and a bunch of imperative commands chained together. Here somebody is taking some number of scans. Actually, one of the motivators for why we're using this other approach is say it has 100 scans and now wants to take 100 of them and fill out the data at each one. The imperative control is very inefficient to maintain, but it's simple for mechanical programmers. Components from the last page that we see here, we have a system voltage table manipulation, a cal file. Set this before we take the scan. So in this case, we have a device called a drag vane. It's a DC field. And we say, okay, put that there. Now we tell it to do a scan dispatch. You tell the DSP to take 5 scans and the lower layer to average those. So just to do very simple imperative commands. Now here's the data query. Say, okay, now return to me the total sum. This is the total ion, the sum of the entire thing. Not shown in the matrix, but with a direct voltage control. Just an example. But that's very inflexible code. If we had to do that to do calibrations, to do automations, to write out step by step by step without being able to recombine anything, we would never get anything done and it would be buggy. And the reason I say that is because it's happened. That people do try to just write line by line a recipe and then it's a code maintenance problem. So the goal we have, we're borrowing from the functional paradigm, is we want to treat everything we do on the system as an operation on the data set and not explicitly control of execution except for little canned routines. Very, very small things like, oh, take a scan or something like that. So we're going to build up instrument control by composing what looks like data operations. I have a set of inputs, and I want a set of outputs. Core tools in this is very elementary for probably 3/4 of the audience. You have to have a map function, which is going to apply a function that you provide to each element of the input. And in the instrument control context, this app can include some of these instrument commands in addition to some command. So we not only say, oh, well, we take it to the third power divided by 4 or whatever, or give me the length of a string. We'll say, oh, we'll take that and apply that voltage to this device over here, and now tell me what the readback is at our mass of 1 kilovolt, for example. But we want to be able to do that. Code the elementary operation of the instrument, set a voltage, read, something like that, and just return numbers or some other data. So put up a map. And a filter operation to take a list of inputs and remove if they don't satisfy a predicate that we provide. So that's another function, and then input sequence of data. And then finally, more useful than you might think in this context is the left fold, the reduce operation. To say, now give me a summary from all of these that's the result of sequential pairwise application. Sums, data projections, even thumbs up or thumbs down can be reduced to reduce operations. So the one thing though, tables is nice, but tables is very greedy. We typically want to do things one scan at a time or one compound at a time on an instrument like this. So instead of operating on tables, we want to define map, filter, and reduce for iterators. And we're using the native Lua iterator, which is a function that returns a function, invariant, and a state variable. That was in reverse order of the pointing, that's okay. The same thing you would provide to the generic for. We want to take a function of that thing you feed to the generic for, and map over each value in sequence, and then have this would in turn be something that you put into the generic for itself. Doesn't have to be implemented with coroutines. In fact, it's a little heavyweight, but it's the most straightforward. Here we're looping over, we reconstruct that iterator that we fed in as an input. Call it again because it's in the for. And now we, instead of yielding the whatever value this yields, we apply that function to each. Very, very simple pieces. Filter, very much the same, except we'll go ahead and we'll pass. We won't yield if we don't satisfy the predicate. So, okay, give us another. And then finally yield when the predicate that we have is there. And of course, if this is, if the input iterator is nil, this for loop breaks, and the lead is nil too, and then everything's done. So it all propagates nicely. And then, is that the same chair for earlier? I say it's
gravity is heavier.
Easy updating here, and distribution is just got a lot narrower, whether or not it's safe. Different chair. Okay. And then finally, a reduce, a little simpler, but we don't have to return until the end. Just running an accumulator over a for loop. And the only thing special about this is we take the native Lua iterator as the input to the for loop and call it again. So this is a function of an iterator. That fun is there because we've got it out. We have namespaces in our instrument code to keep things from stepping on each other. Some Lua-specific considerations for this kind of building up these kinds of libraries. First, that you should be able to support unordered tables as well as ordered things. A typical way to picture a map is one after another, but a map can really just be overall the key. Just use the pairs iterator. Of course, where you need an order like a reduce operation or like an operation to take the first n elements or proceed until you hit something, then you can't do this. But to the extent possible, make it Lua friendly. Don't assume orders, and we don't. Second, that's it's useful to also have around a key value mapping operation to generate a table that's, you provide a function, and then the key, it looks like a map, but you preserve the inputs as the keys, you don't preserve the original keys. And then finally, all of the toys that one would typically use when programming into more functional paradigm have to accommodate arbitrary keys for the tables. So we'll do we'll define something like a zip operation when it's a key zip. So you can provide a key table and then zip the next inputs together using the keys and not just in order, not 1, 2, where you can give them different identifiers, and then in the inside you can treat these like just like any other little table. 5 minutes. So we will skip these examples on time and get to the meat of the problem here. And that is that we want to do compound dependent tuning using these tools. So this whole thing gets calibrated, but we still want more ions. And there are things here that are dependent on specific compound, on the compound of interest. You can handle it in advance. How you tune your ion source, where the voltage should be to get the best response. Gas flows, it's very dependent on unknown chemistry. This piece at the front called the ion funnel trades off a few effects. And it's a very high pressure region, so you get some collisions and some braking, but then you need the RF to be high enough to steer your cloud into the instrument. The fragment pattern you generate is unknown, so we need to go through that. And finally, the collision energies also must be determined empirically. It's a very hard computational problem, especially if you don't necessarily know the full structure of your molecule. So what we want to be able to do is insert and remove optimizations of these things in a customer will. So the design is that we have precursor ion and product ion data structures that are inputs. All of the optimizations then return one of these. When there's a tuning table, it gets updated. The optimizations are composed by function composition. And these optimizations might be procedural code, but we handle all of the state manipulation through a decorator. So we have something called a state setter, which we use the function decorator for each of these things, which reads any information we might have about previous tunings, sets the instrument accordingly, and then returns what the, there's something missing here in the cut and paste, we're supposed to return what the original function call. And then we, oh, that was the decorator that does that, that's good. So yeah, sorry, this is the input to a function decorator, and the function decorator calls the state setter, and then calls your original function. Very useful pattern for isolating states, so we can use these functional patterns. Sample delivery we will skip for time. We can come back to that. So now we can build this thing up using higher order functions. So we'll set up an iterator, we'll map the product optimizations over our products. And you can filter saying, oh, well, now we have a condition saying, well, the user is not interested in ones that are, for example, water loss, because that's so common it doesn't tell you anything. So you kick that out. And something to manipulate the iterator and say, okay, we want the first n, the user wants 5, we cut it off to 5, That's not 5 from the start, it's 5 to get through the filter. And pack that all up. And we can have a precursor optimization that's very similar. And then we bundle up the precursor and the product optimizations using, again, higher order functions. We map source optimizations over the precursor list and map the precursor ion-optics optimizations over the return from that. And then we do the product optimization, which looks at the products iterator that's generated from each of these precursors. And the user can configure this all pretty much at will. The GUI has a table of options. Each checkbox is inserting a function into the composition to build this up. And nope. There. Maybe for my slide, there is a slide. There was a resume slideshow. That's okay. There. This is there was a, yeah, here we go. And play it back. And it's, each step we see here is a run of an optimization function. So it's spray voltage, that's one. It's only a minute long. This is the longest step. Okay, it comes back, sets the state, runs another, and so on. So with that, I will stop for questions. And yes.
So, correct me if I'm wrong, but to me this seems more like you are programming with your system as a state machine state transition. Your approach to the functional style is just to say, how should I iterate over these states? Saying that I add one more variable to my state transition or not.
We are hiding the state transitions and then only we input pure data and we return pure data. So the answer is yes, from a very low level perspective, our state transitions involve in generating and performing the operation. Instead of a mathematical function, we have, okay, now look at the world using this instrument within a particular state based on the inputs. So our function that we're applying, our little functions are state machines. Yes, they put it in a state, read something, return data. But then the larger structure is input an ion with a specific tuning and return an ion with another tuning. So it's multi-paradigm programming, that's correct. Bigger picture functional, smaller picture imperative with a state machine. Anybody else? Thank you very much.